Good morning and welcome back. So we've already seen this video, but I'm going to use it in a different context now. Last time I showed it because I wanted to cultivate a sense of wonder, which I certainly still do, but now I want to talk about it technically. So we're now entering the last part of the section of the course on the physics of animal migration and dispersal and herding. And this is the part that's going to be on the collective motions of animals. And so we're going to watch this video, this time with an eye to thinking about what's going on with this giant school of fish. That's the objective. It's very cool the way the thing healed. There was a wound. You can think of that as a wound. There it is. The wound is, and watch, the wound is healing again. That in itself is fascinating. Now look at this frothing. So that's another thing that's, something really worthy of our consideration. You can see, if we lifted the sea lion out with a crane from that hole, the hole would definitely heal. What determines the shape? There's so many interesting things. So this just really poses the question of over a billion-fold difference in scales. On the top, those are three different examples: schooling fish, flock of starlings over Rome, and then this really, really cool herd of sheep. I especially like the last part of the sheep video, which I'll come on in a second. And then the bottom, we're looking at a C. elegans embryo. And there we see both motors and cytoskeletal filaments. And the question that I want to pose, that we're going to spend some time on now. Okay, check out the upper video. So there's a hole in the fence. There's a gate. You can see from the bottom, you're going to see some dogs coming up shortly. There they are. 3 dogs just entered. And notice what's going on. There's this very interesting backflow of the sheep. They're reflected off of the gate. So on the bottom, as I say, that's motors and cytoskeletal filaments inside of C. elegans, and all of these are collective motions of active agents. So that's the language that I guess I want us to have in mind as we think through the properties of herds. So we're going to use the case of wildebeest as our paradigm, and I want to come back to the wildebeest on a number of different notes, but what we're going to try to do is figure out how to write down a mathematics, a theory, which is a theory that now goes under the name of Toner and 2. Was first, this kind of behavior, this kind of herding, was first seen on the computer in the mathematical sense of the word. In other words, it became a physics question in some ways as a result of work from Vicek, published in the 1990s, in which he observed the existence of long-range order in 2 dimensions, which we refer to as herding. And it was surprising for reasons that I'll allude to, but will not go into deeply. It takes us too far afield in terms of statistical mechanics. But at any rate, we want to try to understand the nature of these wildebeest herds on the basis of a physical theory, a field theory, and this will be the first of many field theories that we will write down in the class. And I'm definitely doing it in the reverse order relative to what I've done in the past. What do I mean by that? Historically, I would be inclined first to show you the simplest of the classical field theories of matter, which is probably the theory of diffusion. So that leads to linear partial differential equations. We can find analytic solutions. We have an intuition from our daily experience about those. But somehow I just got excited about the idea of going straight for real world phenomena and trying to think about them. Although this is gonna put some demands on all of you from the point of view of trying to understand what's going on. So let's talk a little bit about the great wildebeest migration. So as you know, the wildebeest migration takes place in the Serengeti. You can see that it involves the countries of Tanzania and Kenya. And what I can tell you is that it's relatively recent that we came to understand that there is a wildebeest migration that undergoes this clockwise rotation, which you can see here. People knew, of course, that the wildebeest arrived and then that they would disappear. That's not a novel observation. But what they didn't know was that there was this big migration. What do I know about what was known 400 years ago in Africa by African hunters? That I don't know. Maybe there were people that knew and understood that there was this circulation. But what I can tell you is that, to the best of my understanding, in the 1920s, Western hunters went to the Serengeti interested in bringing back large manes, dark manes from lions, male lions. And at that time, that was the real interest of Westerners. And then in the late 1950s, there was an interest. Let me get my order changed here. There was an interest in the behavior of the wildebeest and how many of them there were and what their motions were on the part of this father and son pair. I'll lean over so you can see the names. So Bernard and Michael Grismek. They wrote a book together. They made a film together. And the son was 24 when he died. He was flying a plane doing these counts and crashed into a vulture, and the plane crashed and he died. He had kids already and a wife. And I mentioned that just because, in an odd twist of life, 20 years later, his dad married the daughter-in-law. And there's a lot of pathos to this. This plaque, or I should say this monument on the top of the volcano in the Serengeti says that the son gave everything, both of them gave everything, including his life, to studying the Serengeti. So there's this really interesting facet which is relevant to all of us. We're living through a worldwide pandemic in this very moment. That's why I'm doing these vignettes online. And there was another major pandemic in the 1890s where 95% of the cows in Eastern Africa, in this part of the world, died because of, now we know the causative agent was rinderpest. And the original scientific hypothesis was that the rinderpest, the causative agent, let's just call it that, it wasn't known that it was a virus then, was carried by the wildebeest, and that infected the cows. This is exactly backwards, because in the 1950s, what happened is that there was a vaccine. The vaccine was applied to the cows, and as you can see in this graph, in short order, the wildebeest no longer carried antibodies against rinderpest, which is to say that they were the victims of an infection that was actually in the cows and then passed along to them. So the thing that the father and son pair did, which is shown here, is that they did careful counts. And what I want you to notice is that over, let's say, a 10 or 15 year period, the population went from something like 250, 300 million wildebeest to the now stable 1.3 million. And so what we're going to concern ourselves with is the nature of the herds that these wildebeest form. So our goal will be the mathematization of this kind of problem. And so what I'm going to do next is I'm going to give you a broad introduction to field theory. And with that broad introduction in hand, we will then turn to the concrete implementation of a field theory of flocking and herding, the so-called toner 2 theory.